Okay. The most important thing I think everybody comes today to learn is this is the textbook. If you find a blue and black one at the bookstore, I'm going to scream because it's the third semester in a row they've messed it up. And I was really specific this time. It is 5th edition of Digital Design with an intro to Verilog HDL by Mano. He has effectively written the book on digital logic since before I was born. So great book to have. You need a physical copy. No digital copies. Syllabus on the front desk there as you walk in. He'll figure it out. You will also need a lab kit. This is the same lab kit you need to buy for 201. So if you have not bought a lab kit for 201, you don't have to buy 2 lab kits. You only need 1 lab kit. If you have lost pieces of your lab kit, come see me after class. I've got a little like Amazon wish list that you can just buy cheapy replacement cables. Optional this semester for the first question. I have no idea. No idea. One of the advantages of being me is booksellers will give me the physical copy, and I choose it. It's not, I want to say like $100, but don't quote me on that. Optional is your own digital and analog discovery 2. It is a logic analyzer and function generator. It's not the cheapest thing. It's about the cost of another textbook. I will say that I have received emails from students who've taken the course in the past. This used to be required. It's no longer. We've installed them in all the lab machines. They're super handy to have. If you're a computer engineer, I would say that it's almost a necessity for your career. If you're an electrical engineer, less so. Just a show of hands, computers, electricals. What you guys do, split right down the middle of the classroom? All right. Topics covered. It's stuff. Some of these things won't mean anything to you yet. Exams, homework, labs, attendance. Attendance I take just sort of randomly in class. I usually will give some kind of a quiz, or not a graded quiz, but a question that might tell you if you're doing okay at the start of class. So please show up to class on time. Important dates, things like last day to add drop. The exam dates, all 3 of them are scheduled now, which of course you can't see. Somebody was supposed to remind me. The exam dates are all set today, so you know when they are. Canceled class policy is right below this that says, all right, before every exam, we have a review day. It's a day I have no lecture, no new material. You come in and you own the class. It's open line, usually I think Fridays. It is open line Fridays. How quaint. So you can ask whatever you want, and when you're done asking questions, I can go. But usually we spend the whole class reviewing things and going over what the exam will look like and so forth. If that class is canceled, the next time we meet, that'll be the review session, even though it's scheduled to be the exam. And if the exam is canceled, the next time we meet is the exam. That's it. There is 1 day for makeup. 1 day for makeup exams. It's the last day of class. Okay, so the last day of class, we have no class unless you have missed an exam. And you must have a valid excuse to have missed an exam. All right. 1, and it's a cumulative. So if you miss exam 1, or you miss exam 2, or you miss exam 3, you all take the same makeup. It's cumulative. It's harder. You don't want to take this makeup. So please try to come to exams. Attendance, in-class quizzes, academic dishonesty. This should go without saying. Question?
Are the dates for the final?
Yeah, it's the 12th of Never. Yeah, no final. This should go without saying, academic dishonesty, and yet every semester somebody tries. I'm going to say now don't, because I will find you, and I will, no, that's a different, it really bums me out. Not because I think that you're trying to get one over on me, but it's because you're shooting yourself in the foot. I'd much rather you fail with style than succeed because you borrowed somebody's code from last semester or cheated off your friend. It just doesn't help you in the long run. Just don't do it. So there's a whole, like there's 10, 15 pages on academic honesty and what the types of policies are. 2 bullet points, okay? Sum it all up. If you cheat on a homework, I just give you an F. and you get a little black mark in my book. If you cheat again on a homework, you just get an F for the course. If you cheat on an exam, instant F for the course. I don't care about any of your situations at that point. You have messed up, and you will get an F. Now, that doesn't mean I don't like you as a human. You can come back next semester, and I will treat you the same as if it was the first time you're coming through my course. I don't hold grudges, but you are going to get that F. So, in conclusion, don't cheat. Homework policy. I assign homework in large blocks, all of the Chapter 1 homework, okay, and then I collect it all at once, usually after we finish Chapter 1. I collect it always on Wednesdays. I will never collect it on a Monday. I will never collect it on a Friday. I will always collect it on a Wednesday. Why Wednesday? Because you guys at 9 in the morning aren't the most awake bunch, and you're going to forget, which means that you can go back to your dorm and bring it to me by lab time. Bring it to me on lab, and no late penalty will be assessed. Isn't that wonderful? Professor, you're so nice. I hear you say that in my brain. No penalty, find me the TA. Neat and legible. Make sure that the information is there so that people know what's going on. Keep all this in some kind of a folder, a binder, a notebook. Okay, keep it neat so that it's all together. Other support. There's the Engineering Center. How many people have been to the Science and Engineering Tutoring Center? Super helpful, right? Yeah. If you are running behind and you think that I'm a big scary ogre and you don't want to deal with me, you can go to the Tutoring Center. It's free, and you can set up appointments with people who will walk you through stuff. Yes?
Are you active on my courses?
Nope. No. They're in 217, which is through that little hallway behind the computer lab in 214. However, it's all syllabus. Lost my train of thought. What was I saying? Tutoring Center, behind the hallway in 214. Super helpful. If you have other needs, you can go to the Disabled Student Services Center for Accessing Success. It's located in Pinedale. Usually that's for people who need things like time and a half on exams or a reduced distraction space. And new this semester, or neo-new, because I used to do this and then I stopped and now I'm doing it again, anonymous feedback. This is where you can write me nasty Instagram messages or whatever it is you hip kids do these days. And I won't know who you are. I can't be vindictive by definition. Let's look at it. How do I? Control, click to follow link. That's it. You type. You are snarky and mean. There you go. Done. Anonymous feedback. Okay. Okay. That's the syllabus. Any questions?
Where did you buy the lab?
In the bookstore. If they run out for some reason or something else weird happens, I will go into more detail in the lab this afternoon about where you can get stuff. Again, little Amazon wish list. They're all, a couple of dollars a piece. What's up?
The lab places that we have to go to, whether the same labs.
I'm going to direct you to the syllabus, which I put a great deal of time into writing.
Yeah.
Oh, of course, then oh no, there it is. Where is the lab?
No, I'm not asking where it is. I was asking, there's two different labs. I imagine two different sessions.
You are signed up on Coin for one or the other. So check your schedule. Sorry, I did not understand the question. But that is a valid point. If there is space available, I think we have 42 students right now, which means that there should be, the math will come to me in a second, 42 minus 48 is 6, 3 benches between the two labs that are empty. I don't know if one lab is totally full and then there are 3 benches in one, or if it's 1 and 2 or 2 and 1. So first come, first serve on that if you want to try and do a makeup lab. But at 10 of 150, so at 140, you're going to get an announcement. It's time to clean up. It's time to get out of Dodge because you got another group coming in, and it's rude to shortchange the next group. Okay, So that's a thing. All right. I think that's it. Anything else? Okay. Well, let's have some fun. Someone pick a number between 1 and 5. 3. Somebody else. 4. Wow, we're original today. Come on. Another. 2. Another. 1. Somebody pick another one. There we go. All right. 2.5. We got there eventually. Everybody was going and saying, all right, 1, 2, 3. I'm surprised 5 didn't come out, but 5 is an option. 5 is an integer. 1 is an integer. Syllabus on the front desk as you walk in. 2.5 is not an integer, right? Okay. And this is the start of the difference between digital systems and analog systems. Okay? Digital versus analog. Digital takes on discrete values. There's only so many values between one point and another, whereas analog has infinite numbers between one point and another. So, if I were to try and represent some sort of mathematical function, what's everyone's favorite trigonometric function? Sine. We'll use sine. Sine. I was really hoping nobody was going to throw tan at me because that would have been rough. Syllabus. Sine looks like this, right? Comes up, goes down, comes back again. That's a sinusoidal wave. Now, if I want to choose any point, let's just assume that I'm doing it in degrees, not radians, because I don't want to unnecessarily complicate the math. This would be at 180 degrees. This would be at 90 degrees. This would be at 270 degrees. And this is 360 degrees. So if I said, okay, what is the sine in degrees of 90? You would all look at this graph and say, well, of course, it's 1. Yes, it's 1. And if I did the sine d of 270, that's negative 1. Sine d of 271?
Greater than negative.
Valid. Slightly more. Okay, probably something like, well, hey, I have a calculator. We can do this right now, can't we? Let's find out. What is the sine 271? Sine of 270 times pi divided by 180, 0.82. Who knew? There you go. What I'm trying to illustrate here is that we have a continuous range. I could have asked, what is the sine of 270.5? And in fact, I could have then continued getting closer and closer to 270. 270.25, 270.125. How close can I get to 270?
As close as you feel like writing it out.
As close as you feel like writing it out. 270 point. Can I get any closer than that?
Yes.
Of course, because I could just add another 0. I could add another 0. In any place I didn't leave enough space, I can add more zeros. it's continuous. Now that we have dealt with this, we never have to worry about this again. We are dealing with digital values. This is digital logic. Okay? And in fact, it gets even simpler. But we'll start with digital numbers. All right? So I'm going to make this a little bigger here. Here's what sine was supposed to be. Yes, I'm playing fast and loose with my x-axis scale, but this is what it's supposed to be. Because we can only deal with discrete values, there are only so many places that I can grab numbers. And there's only so many places that I can get y values. Okay? So as I go along, I'm going to get a series of samples. For you electricals, you're going to be seeing this kind of a diagram over and over again. But as digital logic, this is just to illustrate what we're not going to be doing. So each one of these samples has a value. Okay? If we were to try and reconstruct this, however, what we would probably end up seeing is not a sine wave. We'd see something that looks a little bit more like this. A little bit of a staircase effect. Okay? And if we were to add more points, let's double the number of points. The staircase would get a little less steep. Do it in yellow now. A little less steep, and a little bit closer to approximating what a sine wave is. Now, even this is more than we're going to get into. We can't handle numbers like this. We're going to handle the most basic case. Start writing our number system here. 0. And I hear some of the smarter Alex of you, 0 and 1. That's it. With these two digits, we will represent all the other digits in the world. Now, with 0 and 1, you can represent two things. It's called binary, because bi meaning 2. These are the only two digits we need. And today we're going to learn to count in binary. But before we learn to count in binary, I know that this may seem like I'm treating you like children, and that's because I am. Everybody has some phalanges, some more than others. Does anyone have any less phalanges than others? Because that will be useful as a demonstration. We all have 10 phalanges then in the class? False. How many phalanges do we have? Nope. A lot. We've got fingers and toes. They're all phalanges. Dancing phalanges. Yes. When we learned to count, we counted on our fingers to start, right? We counted 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And 10 is sort of interesting. 5, 6, 7, 8, 9, 10. Did I miss my face? Oh, my face is over there now. How delightful. 10 is interesting because it requires more than one digit. And in fact, we start reusing digits at this point. We've reused the digit 0. So we have in the decimal system 10 digits. And when we exhaust those digits, we add another place. What did we call this place way back in grade school? This was the ones place. What was this place called? The tens place. And then the next place, what was it called? Hundreds. After that, thousandths, 10,000s, 100,000s, millions. The interesting thing about those place values is 10 could be thought of as 10 to the 1. I don't know why you would, except for this example. If you were writing everything as a power of 10, grab a syllabus while you're at it on the front desk. 10 to the 2 is the hundreds place. 10 to the 3 is the thousands place. 10. Did I write 12 to the 2? Did I say 12 to the 2? No. It's early yet. There's many mistakes to be made. 10 to the 4. What we're seeing is an increasing power of 10. What about the ones place? What's that? 10 to the what? 10 to the 0. So in the decimal system, every place is a power of 10. And to count in decimal, we use all of the digits that we possess until we run out of them. Then we restart back at 0 and increment the next highest place. Okay, well, let's try counting in binary then. So here we go. The first number in binary is 0. And we go until we run out of digits. So we go 0 and then 1, and then we've run out of digits. That's okay. Well, we know what to do. Based on what we do in base 10, we reset that digit to 0, and we increment the next guy. Okay, so 10. And then we just keep on going, right? So we increment, that's 1, 1. And now, well, we run out of digits again. This is going to get old fast. So we increment this 1, or rather we reset it to 0. And we increment this guy, but this guy's already at 1. So we've run out of digits for him too. So I guess we set him to 0, and we put a 1. Just like going from 99 to 100, right? When you increment the 9, you reset it to 0. Then you increment the 9, you reset that to 0, and you increment the next place. So what's the next number? 101. What's the next number? 110. What's the next number? 111. What's the number after that? 1,000. All of those are incorrect answers because that's not how we say numbers in binary, but it gets the point across, doesn't it? So I want to point out a couple of things that make counting in binary pretty simple. First off, look at the least significant place. Notice that it repeats over and over and over again. Now, looking at the higher places is a little bit harder because they don't exist in some of the numbers, right? Well, for our purposes, we're going to always assume that if it's not written, it's a 0. And you'll see binary numbers written like this fairly often. Even though you don't use those more significant bits, you still write them in. You choose a number of bits, usually some multiple of 4, 4, 8, 12, 16, 32. And you write those zeros in all the time, mostly so that you can keep things aligned nicely. So let's look at now the next highest place. Here, it's 2 zeros, 2 ones. 2 zeros, 2 ones. In the next row, 4 zeros, 4 ones. Probably if we were to continue on, it would also do 4 zeros, 4 ones over and over and over again. And in the next row, 8 zeros. And we stopped, but I'm going to tell you that there are 8 ones following this. So here it's 1 0, 1 1. Here it's 2 zeros, 2 ones. Here it's 4 zeros, 4 ones. Here it's 8 zeros, 8 ones, which is convenient because unlike the decimal system, we don't have powers of 10. We have powers of 2. It's the binary number system, so each value is a power of 2. And 1, 2, 4, and 8 are 2 to the 0, 2 to the 1, 2 to the 2, and 2 to the 3. Okay, 2 to the 3 is 8. If you want to take any of these numbers and figure out what it is in decimal, for example, if I gave you 1011, and I said, what is that decimal number? Well, it's really easy because each one of these is worth a certain amount. This 1 is worth 2 to the 0. 2 to the 0 is 1. This 1, oh, you can't see it. Oh, yeah, you can. This 1 is worth 2 to the 1, which is worth 2. This 0 is worth exactly 0. It's not worth anything. And 2 to the 3 is worth exactly 2 to the 3, which is 8. So you add those up, and your end result is, I'm bad at arithmetic in the morning, 11. I'm apparently quite a popular person. I don't know what's going on here. Yes?
So are you using the base 2? And you might have already said this, but are you using base 2 because you're using binary, whereas if you've been converting hexadecimal, you're using base 16?
I'm going to ask you to give me like 20 minutes. It's fine. It's great. Awesome. Don't feel like you can't try to jump ahead. It may segue nicely into what I'm about to do. You're just a little bit ahead. So binary is one of those things that you guys are not going to be able to just sort of forget. I don't want to say forget, but not learn. You need to know about binary. Specifically, you really need to know how to count to 15 in binary. You need to know how to count to 15 in binary, and I'm going to do it right now. Not in this hard yellow color, though. That is the first number. Now, I've got two ways of writing this. I can go ahead and write each number 0000, 0001, 0010, 0011, 0100. Or I can take what I know about the way counting sequences work, and I can make my life a lot easier. Since I know that I have the 1's place, the 2's place, the 4's place, and the 8's place, I can take a shortcut. I know that in the 8's place, I'm going to have 8 zeros and 8 1's. So that's 5, 6, 7, 8, 1, 2, 3, 4, 5, 6. I ran out of space. 7. I need to find a space for it. Movie magic. Here we go. 8. And that's not being blocked by my face, right? So that's 8 zeros, 8 1's. And then I can write 4 zeros, 4 1's. 4, 1, 2, 3, 4. And then 2 zeros, 2 1's. 0, 0, 1, 1. 0, 0, 1, 1. 0, 0, 1, 1. And then in the least significant case, it's every other. So 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. This is every combination of 4 digits of binary. There is no combination that I have not written down that is 4 binary digits. Go ahead, take a second. If you can find one, it means I've made a mistake. Go ahead. Anybody want to try? Okay. Now, alone, this list of numbers doesn't do you any good. You need a translation key to decimal. And if you write it out like this, it's really simple to create the translation key because it's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. Super awesome. Now that's only going to take you so far. Okay, the binary number system is only one of several number systems that we're going to use. The reason we don't use binary all the time is because as humans, we have wrists, and wrists get carpal tunnel. So we don't like to write out long sequences of numbers. So we use shorthands. Before we talk about those shorthands, though, we've only gone one way. We've got the base 2 number system. We've got the base 10 number system. We've talked about how we go from 2 to 10. You just look at each place value and multiply by its power. It would be nice to know how to go from 10 to 2. And this is also pretty simple. It's very straightforward. Okay, if I have a number, for example, 112, which I pulled out of thin air onto the page, and I want to convert this base 10 number to base 2, all I have to do is a handstand. and divide. I have to do a handstand and divide. Normally when dividing 112 by 2, we do something like that. 2 into 11 is 5, 10, 1 left over, bring down the 2. 2 divided by 12 is, or 12 divided by 2 is 6, 6 even. That's division. When we divide on our head, we're still doing the same thing. We need to get 56. Okay. And in this case, yeah, there's nothing left over. And I'm just going to leave it in the old way where we don't go to decimal places. I hated that part of school anyway. We'll just leave the remainder there, the remainder of 0. But we're going to continue to do this. Divide 56 now by 2. 56 divided by 2 is 25 plus 3, or 28, with a remainder of 0. In fact, when you divide an even number by 2, it's always going to have a remainder of 0, right? So we divide by 2 again. 28 divided by 2 is 14 with a remainder of 0. 14 divided by 2 is 7 with a remainder of 0. 7 divided by 2 is 3 with a remainder of 1. I'm glad somebody said that because I was in my head, I was going 3 with a remainder of 0 because I got into that pattern. It's 3 with a remainder of 1. What is 3 divided by 2? 3 divided by 2. It's 1 with a remainder of 1. I can always check myself by taking 1 times 2 plus the remainder is 3. Yep. And then what's 1 divided by 2? 0 with a remainder of 1. And that remainder of 1 cannot be forgotten. This is the process you will use for converting any base 10 number to any other base. You take the base that you're going to as the divisor and the number in base 10 as the dividend, and you do this division until you reach 0. When you reach 0 as the quotient, you stop. And then you have this list of remainders. And remember I said we were doing division on our head, right? Well, obviously that means we have to read the number backwards. So I'm going to read from the bottom up. So when I take this number, 1, 1, 1, 0, 0, 0, 0, this is a base 2 number. And to illustrate that it's a base 2 number, we use a vertical bar and then a subscript with our base. So this is this number, base 2, is equivalent to 112 base 10. They are equal. Okay. Now, we could also go back and check this. All right. Checking this is pretty simple. Let's just take this for a moment. This is our number that we want to check. Now, before what we did, we just kind of took a shorthand path. I showed you the short way first, and it works for small numbers. I just kind of wrote the powers up above. 1, 2, 4, 8. What comes after 8? 16, 32, 64. Anybody ever play 2048? That was a fad for like 5 minutes 4 years ago. Okay. That was just a game that just did more and more powers of 2. It was awesome. Anybody have a high score they want to share? Because I beat it. All right, that's fine. So this is not quite as simple. You got to bring some stuff around. Here's how we do it in a very systematic way to reduce errors. It involves a lot of L's. This is going to be 0 times 2 to the 0, 0 times 2 to the 1, 0 times 2 to the 2, 0 times 2 to the 3, 1 times 2 to the 4. And you may be thinking, this is dumb, Professor. I get it. We understand. You just take and you get the powers of 2 to the 5. Yeah, that's right. But for larger bases, this does become important. So we're going to talk about it this way. So this is what we do. We take each one, we write it. It takes up a little bit of space on the page, but it's very easy to see what's going on here. And then we can say, depending on how many steps we're skipping, we can either say this is 0 times 1 equals 0, or we can just kind of ignore the ones that are 0. This is 1 times 2 to the 4 is 16, which is equal to 16. 2 to the 5 is 1 times 32. 2 to the 6 is 1 times 64. So we have 16 plus 32 plus 64. And we do that math, and hopefully we don't mess up. That 6 plus 4 is 10, plus 2 is 12. 6 plus 3 is 9, plus 2 is 11. What did we start out with? Did we do everything correctly? Well, we ended up with 112 base 10, and that's what we started with. So we've just checked our answer, forward and backward. So now we know that there is this number system called base 2. There is this number system base 10. We've always known about base 10, but now we know how to get to base 2 from base 10 and how to get from 2 back to 10. So this involves multiplication. This involves division. It's not the only number system, though. We're going to talk first about, let's see, how much time do we have? We got enough time. We're going to talk first about a number system called base 16. Base 16 is sort of an oddity from the number systems, the other number systems that we talk about, because base 16 has 16 symbols. And normally we've only ever dealt with at most 10 symbols. Base 2 is a subset of the base 10 symbols, right? It's a subset. They use the same numbers. Base 16 uses the same numbers, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then they need still 5 more symbols. So they take them from the most readily available place, the alphabet. A, B, C, D, E, and F. Sorry, I ran out of space there. So those are the 15 symbols in hexadecimal. It's 16 symbols, 0 being one of the symbols. Okay. Now, going back for a moment, we had that list of the first 15 binary numbers. And this is why you need to know the first 15 binary numbers, because the list of hexadecimal numbers fits very nicely on here. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. A, B, C, D, E, F. So, if you have a small number, something less than 15, you can consult the table. I highly recommend getting this tattooed on the inside of your eyeballs. Make flashcards, do whatever you have to do. Memorize this. It's 15 little facts, okay? And it's going to help you, it's going to speed up your problem solving in this course by orders of magnitude. If you can just have this at your fingertips and not have to look it up, not have to derive it. Okay, so base 16 has an advantage because 4 binary digits fit inside of a single hexadecimal digit. In fact, some 2-digit decimal numbers also fit inside of a single hexadecimal digit. Now, we talked about how to go from base 10 to base 2. We use division. And then we said, okay, to get from base 2 to base 10, we use multiplication. The same applies for base 16. Base 16, when we go to base 10, we're going to be using some form of multiplication. And we can go from base 10 to base 16, we're going to use division. I'm leaving a space over here, by the way, just for base 8. It'll come back to it. All right, let's do an example of base 16. Let's start by taking that same number, 112, because it seemed like a nice number, and we're going to convert it into hexadecimal. To do that, you divide by the base, 16. Now, 112 divided by 16 is what? At this point, I have to cheat because otherwise I'll make a mistake and slow the course down. So 112 divided by 16 is 7, with a remainder of 0. What is 7 divided by 16? This one's easier. 0, remainder of 7. And at this point we're done. Okay? Converting to higher bases from base 10 is a lot faster because there's less to do. And then, so what is the answer? The answer is what base 16? 70, because we read from the bottom up. 70 base 16 is equal to 112 base 10. And we can now check that too, can't we? We can do the same thing. We can take 70 base 16 and figure out, is it really 112 in base 10? And to do that, we're going to use that same process. 0 times 16 to the 0, 7 times 16 to the 1. So 16 to the 0 is just 1, so that's 0 times 1. And 16 to the 1 is 16, so 7 times 16. I cheat again. Oh, look, it's 112. So there we go. So base 16 is really not that crazy. Let's do something more interesting. Let's do another one. 240 base 10 equals what in base 16? Go ahead, give it a try now. Take 2 minutes and do some math here for me. All right. So what is 240 divided by 16?
15.
It's 15 with a remainder of 0. And what is 15 divided by 16? With a remainder of 15. So the answer seems like 150. In 1. The answer is not 150. Don't make this mistake, okay? Because the answer is not 15 appended to 0. It's whatever hexadecimal digit is the same as 15. If you don't know that, you go back to the table and you say, okay, what is, well, the table's a little far away. 15 is an F. Okay. So since 15 is an F, this answer is F0 base 16 is equal to 240 base 10. Okay? With the remaining time, I'm just going to go over that there does exist one more base that is common. We could have any base. We could have base 2, base 3, base 5. Okay? Base 8 is another common one. It's kind of a middle ground between base 2 and base 16. Base 8 has 8 symbols. They go 0, 1, 2, 3, 4, 5, 6, 7. So the thing to know is in any base, that digit doesn't exist as a symbol. So base 8 doesn't have the symbol 8. Only has 0 through 7. Base 4 only has symbols 0 through 3. And so on and so forth. So that's base 8. And converting is the same way. Okay. Now, we've talked about 3 bases, and going to base 10 from base 8 requires multiplication. Again, by powers of 8. 8 to the 0, 8 to the 1, 8 to the 2. Going from base 10 to base 8 is dividing by 8. 16 divided by 2. Okay? Whereas multiplying, we multiply by 8 to the n, or 2 to the n, or 16 to the n. So if I gave you a base 2 number, and this is preview of coming attractions, we're going to cut it here. If I asked you to go from base 2 to base 16, right now the only thing we could do is convert base 2 to base 10, and then convert base 10 to base 16. So when we come back next class, we will talk about a shortcut. If you did not get a syllabus, are there any extras lying about? Do you have an extra? All right. 2 extras up at the front desk. There is lab today. It is another show and it's a show and tell lecture. Do show up. You don't need any material at the notebook. Oh, I can't close the computer yet. It's still recording.